Hello, class. Okay, so this lecture is going to kind of tie into the last one. So we're talking about transfer of charge. But we're going to talk about a particular device, mainly, called an electroscope, which I've kind of drawn here. So this was an early device that was used to detect the presence of electric charge. And it also gives an idea of how strong this charge is. So how it works, let's start at, we have, this is a conducting rod. So it's some kind of metal, which conducts electricity. It could be like iron or copper or something. Here, G, we have gold foil, which gold has this remarkable property that you can, pound it into extremely thin sheets, or like pull it into wires. Kind of an unusual metal, very malleable. Like the type of foil we'd use here would have a thickness of about 0.00001 inch. So extremely thin foil, which makes it extremely light. And so there's two pieces of gold foil that hang here. Now, if you look at it, so like you have, it's suspended by this rod, and here's a gold foil. It can rotate about like this rod that's supporting it. So you have these two thin sheets of foil that can move very easily. They can rotate. Now S is an insulated stopper. So picture rubber, and V is just a vessel to contain it, like a jar. You could have a glass jar with a rubber stopper. And again, this is an insulating material. So if you apply charge to the conductor, that'll keep the charge from leaving the conductor. And it's contained in a vessel because this gold foil is so thin that even a tiny air current could cause it to move. So this is the idea, or this is kind of the basic electroscope. Now, if we were in class, I could actually show you these because we have them in the lab. And this is one of the earliest devices used to detect electric charge. And the way it works is this rod and the gold foil, these are conductors. So if we apply a charge by just, say, touching a charged object. So let's say we have a positively charged object, and we touch it to the conducting rod. It's got a ball at the end. And, I'll talk more about later. Like if you have a sharp point, charges can bleed off. So that's the reason we'd have this ball at the end. So let's say we transfer some of the charge from this rod to this conductor. Now the thing about conductors is the charges can flow fairly easily through them. And charges, like charges, do not like to be close to each other. They repel each other. And so if you put the charge here, like we apply it to the end of the rod, it's going to spread out. Now, it's going to go throughout the entire rod, and some of it's also going, so say this initially had a lot more charge on it. So again, the total number of charges is fixed. Charge is conserved. And so someone's going to transfer here, and then it's going to spread out, because that's just what happens when you apply charge to a conductor. And so some of the charge is going to flow down to these two individual sheets of gold foil. And because they're white charges, they're going to repel and separate. Now, the more you charge this object, the greater the separation is going to be, because there's a repulsive force. But again, say like this is a side view of this sheet of gold foil. Say here's the center of mass. We know that gravity is pulling it back down. It's applying a torque, causing, say, clockwise rotation, where the repulsive force is applying a torque in the other direction, and they're going to balance each other out. But the greater the charge, the greater this force, and so the greater separation you're going to get. Now, the thing about the electroscope is if you replace this positively charged object with a negatively charged object, you will get the exact same effect. So again, if we just apply a negatively charged object to this, we just replace all these positive charges with negative charges. Again, they're going to be a light charge on the plate, so they will be separated. And so an electroscope can detect the presence of a charge. It can give you some idea of how strong the charge is, but it won't tell you what type, if it's positive or negative, because they have the exact same effect. Now, there's another way we could charge this object without directly touching it with the charged object. So, this is called charging by induction. Now, we don't have to touch it with the charged object, but at some point we'll have to touch it with something else. But let's just start out with an electroscope. And let's say we hold a negatively charged object near it, but we don't touch it. Is this going to have any effect? Well, there's not going to be a transfer of charge from this rod to the electroscope. However, there will be an electric force. Charges exert forces on other charges, and there are charges in this conductor. There's just an equal number of positive and negative charges. And so what's going to happen? Now, let's talk a little bit about metals, like, say, iron or gold or copper, whatever you're using, aluminum. The atoms form this kind of crystalline structure. Depending on what type of metal, they have different shapes, like how the atoms arrange themselves. But it's like every atom has its fixed place in the conductor, like relative to each other. There's different types. You can have a simple structure where they just form like, the atoms would form the corners of a cube. Very simple structure, all sorts of different types. But anyways, the atoms are basically fixed in place, and so protons are not going anywhere. However, electrons are free to move. Now, I should be a little more specific about that. We have a metal here, and so it has an equal number of protons and electrons. And typically what happens in a metal is every atom will kind of give up one electron. Let's say copper, for instance. Copper is atomic number 29. I believe. I should double check that. For some reason, I'm thinking it could be 27. I don't know if I have a periodic table with me or not. But anyways, doesn't matter too much. Let's say we have Z equals 29. So copper is either 27 or 29, but let's say it's that. And so every atom has 29 electrons. However, one of them is very loosely bound to the atom. And if you apply a force to it, it could easily leave that atom and just walk. It's kind of stuck to the metal itself. If you try to remove it from the metal, you're leaving net charge on the metal, and you have you leave a net positive charge on the metal, which will attract the electron. Now, it's possible to remove an electron entirely from the metal, but it would take a stronger force than what we're talking about here. So the electrons are confined to the metal, but they're free to move around. Positive charges are not free. So what's going to happen is we're going to have a flow. The negative charges are going to move down this thing and get as far down as possible. They're going to move down towards this end. And this conducting rod and the gold foil together, they're electrically neutral. So that's going to cause a separation of charges. So again, this object was neutral before, the conducting rod and the gold foil. It's still neutral, but the charges are separated. And so now what happens if we remove the rod? Well, the electrons are free to move back. They're going to be attracted to the net positive charge left at the top of the electroscope, and they're going to flow right back. So right now we hold the rod here. We have a separation of charges. If we move the rod, they just go back to normal. However, what if we have the rod here, And what if we attach a metal wire, or you could touch it with your hand, either way. But let's just say we have a metal wire going into the ground. It looks like that. What's going to happen is that the negative charge is going to flow down this wire. And so, let's say we do that. The charge flows down the wire. Now, that'll leave this whole thing with a net positive charge. Because we're repelling negative charges, we're going to have negative charges flow down the wire. That would leave a net positive charge on this conductor. If we remove the rod, that charge will flow back because it's being attracted. This will be a net positive charge. We have a free source of electrons that's easy to move. They're going to come back and we'll be neutral again. But what if we leave the rod here and we do this? We leave a net positive charge on the oscilloscope, the electroscope, and then we remove the conducting wire, and then we removed the rod. So basically we've charged this electroscope now. We had a negative object here, and that left a net positive charge on the electroscope. If we had a positively charged object, that would leave a net negative charge on the electroscope. And again, we did have to create a way for charge to leave the conductor entirely and then not be able to come back in order to make this happen. But at no point did we touch the rod to transfer charge directly. At least not with the charged object. We did have to touch it with, you could use your hand and let the charge flow through you, or just like a metal wire going into the ground, something like that. So that's called charging by induction. So again, this lecture was a little bit shorter, kind of ties into the last one. Maybe I should have just combined them, but I want to stay consistent with what's in the notes. So that'll be it for this one.